Hello, in this video, we will try to learn about the structure, nomenclature, and synthesis of ether. Okay, when we say ether as a functional group, these are the compounds with the general formula ROR or R prime, where oxygen is connected with either two alkyl group, okay, this R and R prime and R prime can be either alkyl group or they can be aryl group. So oxygen is connected with either alkyl or aryl group. We consider that as ether. And for example, one when we have two CS3 group connected to oxygen, this is one example of ether. Or you can have the aromatic ring, for example, attached with the oxygen, and then say here CS2 CS3. This is another example of ether. Now talking about the structure, if we look this ether molecule very closely, then what we can see is ROR prime. Here the oxygen possesses two lone pair of electron. And considering these two lone pair of electron, the oxygen is here sp3 hybridized. And with sp3 hybridized state, this ROR prime bond angle, the theoretical value needs to be 109.5 degree. That means it should be sp3 hybridized angle 109.5 degree. But however, because of this bulkiness of this ROR R group, then this angle is little bit expanded, little bit bigger than 109.5. In, say for example, in CS3O CS3 or in dimethyl ether, this COC bond angle goes somewhere around 110 degree, which is very close to 109.5. So that is the angle that they display. Okay, so this is the structure of ether. Now, because since the oxygen here is connected to two carbon containing group, this oxygen is not capable of forming any no hydrogen bond is involved, can involve no S bond. Because of the lack of hydrogen bond, they usually possess less melting point, or let's say less boiling point. Melting point, boiling point will be less. And talking about the hydrogen bond, because of the lone pair of electron, because of lone pair of electron, these this oxygen can be hydrogen as bond um, acceptor, but since it does not have any hydrogen, but therefore it has no hydrogen bond donating ability, no S bond donor, so it cannot show the hydrogen bonding. And because of this lack of hydrogen bonding, these are usually insoluble insoluble in polar solvent like water or methanol. They will be insoluble. However, they will be soluble in non-polar solvent. And the ether themselves, because of their inertness, these ether are a very can behave as a very good solvent. Okay, very good solvent. Uh, but the 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 problem is, though they can act as a good solvent, the problem is the solubility. Because of their non-polar nature, the most of the salt will not dissolve in ether. That is one big of a problem. Therefore, the chemist has developed what we call is the crown ether. That ether in the cyclic format, that is what we call crown ether. And uh, so that this crown ether will be acting as the polar solvent, and the ion can be solvated. So those crown ether are of a variety of the different type, depending upon what type of ions that needs to be dissolved. Say for example, one is say this two oxygen here, this oxygen here, here is other oxygen. So this is one example of crown ether. Okay, here are four oxygen, four ether molecules are combined together forming a crown like structure. So this ether, this crown ether is named as, so you got to know how to name this. So in this structure, how do we count here is find out the total number of atoms that forming this cyclic system. Say, let's start with this oxygen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 atoms are involved in this cyclic system. So we can name this as 12 crown. And out of these 12 atoms in this ring system, these four are oxygen. So this is 12 crown 4 is the name for this crown ether. Now with this 4 oxygen, it will form the pocket. This is the pocket that is generated. And in depending upon the size of this pocket, we can uh, it can bind different type of metals. Say for example, for the 4 oxygen, the appropriate atoms that can be adjusted here is lithium can coordinate at this 12 crown 4. Okay, so if we wanted to adjust the sodium metal, then we will have to make it the little bit bigger pocket. Say for example, this one here. Let's try to make this one here. If we look at this, so the 5 oxygen, and then these all are the carbon atoms there. So that means if you count all these atoms, this is 15 atoms together, crown, and 5 are oxygen there in the ring system. Okay, and then this pocket is somewhat bigger, and it will be able to accommodate the sodium ion on this 15 crown 5. So this is how for sodium ion 15 crown 5 is the best pocket for adjusting. So this type of ether that contains many oxygen atoms forming the cyclic system, this will act as the polar uh, type of the solvent, and it will form the crown ether complex. Crown ether complex will be formed, and that will uh, help to solubilize the uh, metal salt. Like the since lithium ion, sodium ion are coordinated in the crown ether system, then this kind of salt can be solubilized. For example, if we need the potassium, then we will need 18 crown 6. Similarly, we can develop 18 crown 6 for potassium, 15 crown 5 for sodium, for 12 crown 4 for lithium. So these are different types of crown ether that has been developed to make that as the uh, somewhat polar type of the solvent because of inertness of the ether. This crown system is developed to make that as the polar solvent. And another beauty of this ether compound is that uh, because of the lone pair of electron in oxygen, lone pair of electrons in oxygen, they can stabilize the metal complexes. For example, if you have the Grignard reagent RMGBr, this ether can easily coordinate with the metal, and it can stabilize the Grignard reagent, like organometallic reagents can be stabilized. That is why ether are very popular as the solvent system. Okay. Now the next point that we wanted to discuss here is about the naming of ether. Uh, for naming this simple small type of the ether, the common system is very popular. common system of naming ether is very popular. And in the common system, ether are named just by giving, the say for example, you have CS3O, CS2, CS3. On one side of this oxygen there is a methyl group, on the other side there is a ethyl group, and we, in common system, when we name this kind of ether, we just name this alkyl group in alphabetical order and put ether as the suffix. So this will be ethyl, E comes first, methyl ether. Simply we put ether at the end, ethyl methyl ether. Okay. Similarly, for example, if we have this is the uh, ether that we wanted to name. This is ethyl, this is isopropyl group ether. So this, the name of this ether will be ethyl isopropyl ether. That is how we name the ether in the common system. Say for example, if you have this, the ether, and you are asked to give the name of this ether, this group is called T-butyl. This group is called isopropyl. Okay, isopropyl. So the name of this ether will be T-butyl isopropyl ether. Okay, this is butyl. That is the B is the initial here. T-butyl, and isopropyl ether is the name for this compound. So this is how the ether are named in the common system. And in uh, IUPAC system, which is not very commonly used. So say for example, if you have this kind of ether and we wanted to name this by IUPAC system. So first of all, we find out the longest carbon chain. So this is the 3-carbon chain. And on carbon number 2, we have the methoxy group and we have the methyl group. So you have carbon number 2 has methyl and carbon number 2 has methoxy. 2-methyl, 2-methoxy ether. So 3-carbon chain, that is propane. 3-carbon chain propane, and carbon number 2 has methyl group, carbon number 2 has methoxy. 2-methyl, 2-methoxy propane is the IUPAC name of this compound. Okay, this is how the ether are named in the IUPAC system. Okay, now the next term is we need to discuss about the synthesis, or you can also say preparation. Preparation, or you can say synthesis of ether. One very popular way to prepare ether is what we call Williamson's ether synthesis. And in Williamson's ether synthesis is first of all we have alco oxide. This is RO group, we call that as alco oxide, and we will discuss that where this alco oxide can be obtained from. When we have alco oxide and reacting with some kind of alkyl halide, it will undergo SN2 type of the reaction. So the X will be a leaving group, and we have RO, say this is your R prime, and X will leave as a leaving group. So this is how we prepare the ether by Williamson's ether synthesis. The key question here is, how do we get this alco oxide? Okay, how do we get this alco oxide? Obviously, this alco oxide is obtained from an alcohol. Okay, and in alcohol, this hydrogen needs to be removed, right, as a proton, the deprotonation of this alcohol. But you know that alcohol is less acidic with pKa very close to 16. So in order to remove this hydrogen, we need a very powerful type of the base, or say we can use certain type of metal like sodium Sodium will grab the hydrogen